Hello everyone, here I wanted to discuss the Laplace transform and a few properties thereof. But first let's just take a look at what the definition of the Laplace transform is, and it basically says the following by definition. That if you take Laplace of any function f of a variable t, then, well, it's by definition equal to this integral, this improper integral, from 0 to infinity of that function in terms of t, times e to the negative s of t, dt. Now here, since t is kind of our quote-unquote dummy variable, in other words, we'll take the antiderivative with respect to t, but then we'll plug in values for t. So t goes away. But here we have a new variable s now. So really what Laplace kind of does is it takes a function in the t domain and gives us a new function now in the s domain. Now very often t and s are referred to as time and frequency domains. I'm not really going to worry about any of the applications of Laplace here, but let me just say there are a lot of applications, specifically with electrical engineering, that you'll see with the Laplace transform. But for right now, mathematically, just purely mathematically, this is what we do. So we have a function, we plug it into this integral form, and then we can solve that integral, and then we'll get a new function, but now in a new variable s. So in fact, some people like to think of this action kind of like what you would see in derivatives. With a derivative, you have a function, you take the derivative, you get a new function. Very similar idea here. You have a function, you take its Laplace, you get another function. The only difference really here, though, opposed to derivatives, is that we change the variable from t to s as well. Anyways, let's move on. I have these three examples I want to go over, and then we'll kind of generalize a few things. So if we want to find Laplace of 1, then we're going to have the integral from 0 to infinity of 1 times e to the negative st, which is just this. Now, s, yes, is a variable, but in the eyes of t, we're going to treat it as a constant. So imagine that s is a constant. Now, the antiderivative of e to anything is itself divided by the derivative of the power, so long as the derivative of the power is a constant, in which case here, the derivative of negative st is negative s, which is a constant in the eyes of t. In other words, we have to divide by negative s. Which makes sense, because if you take derivative of this, you get itself times the derivative of the inside, which is negative s, and the negative s is cancelled, so you indeed get e to the negative st. Right. You can also do this by u sub, but hopefully we've seen this already by now. Now we want to evaluate between these limits 0 and infinity. And you may think, well, we have to use limits here when you plug in infinity. And that's certainly true, but I'm going to do that a little less, I guess a little less formally. So I'm going to do it like this. So we're going to set, we're going to plug in infinity first. So we get 1 over negative s times, so let's do that after the evaluation. So something like this, really. That makes sense? Equals 1 over negative s times, when you plug in infinity, you get, well, e to the negative infinity, minus when you plug in 0, you get e to the 0. Now, of course, e to the 0 is 1, and e to the negative infinity is kind of an incorrect way of writing things, because you don't really plug in infinity, you find limits as something goes to infinity. But we know that this really means the limit as x goes to infinity of e to the negative x. And we also know that e to the negative x is 1 over e to the x, and e to the x goes to infinity as x goes to infinity. So in fact, this whole limit goes to 0 because the denominator blows up to infinity. So e to the negative infinity we can think of as just being 0. And e to the 0, of course, is just 1. So in fact, we get 1 over negative s times negative 1, which in turn is just 1 over s. So Laplace, there we go. Laplace of 1 is 1 over s. Fantastic. Now, what about Laplace of t? This is going to be a little more complicated, but we'll kind of do it in the same way. Let me erase this just for space here. All right. So now, again, we're going to use the definition here. So we have the integral from 0 to infinity of our function, which is t, times e to the negative st, dt. Now, in this case, we actually have to use by parts, really. You could actually think of using the tabular method if you like. So remember how that works. You have a derivative column and an antiderivative column. We're going to let t be our derivative column starter, and e to the negative st be our antiderivative starter. We take derivative of this until we get to 0, take the antiderivative of this until we get caught up to the 0. We know the first antiderivative based on the way we did the first example, and then again, kind of in a similar fashion, if you take the antiderivative again, you divide by another negative s. So in turn you get 1 over s squared, of course, because negative s times negative s is just positive s squared anyways. Negative times negative is positive, of course. And then by the rules of tabular method, you multiply diagonally like this and alternate the signs positive, negative, and so on. So now what we end up getting here is negative 1 over st e to the negative st minus 1 over s squared e to the negative st. Okay, good. We want to evaluate this between 0 and infinity. Okay, now something happens. Now when you plug in infinity, remember that e to the negative infinity goes to 0, but here you actually have infinity times e to the negative infinity. If you wanted to work that limit on your own, you would write it as, well, t over e to the, you can think of it like, kind of like as x over e to the x, something like that. Because it's negative power means you have e to that in the denominator, and s is a constant, so you can kind of ignore that. But long story short, this will go to 0 when t is infinity. Even though there's a t in front, so let me just write it out more formally like this. If we take the limit as t goes to infinity, you can actually use L'Hopital's rule to show that this actually goes to 0. Because if you plug it in directly, you get infinity over infinity, which allows you to use L'Hopital's rule. And by L'Hopital's rule, you have derivative of the top over derivative of the bottom in the same limit, and you end up getting 1 over s e to the st, but remember s is a constant. And also remember that e to the t goes to infinity as t goes to infinity. This, of course, kind of assumes that s is non-negative, so we are assuming that here. Otherwise, this idea doesn't make any sense at all. Because if s is negative, then this can possibly be in the numerator, not in the denominator, and the limit won't actually be finite, and it'll be an infinite answer. So we're assuming that it's the case that when you plug in infinity, you get 0. In fact, that'll always happen. So here, for this evaluation, we're going to get 0 for the first term, minus for the second term. When you plug in 0, you get negative 1 over s times 0 times e to the 0, which is, of course, just 0 itself, because it's multiplied by 0, minus 1 over s squared e to the 0, and remember, e to the 0 is just 1. So we get negative 1 over s squared, so this is actually just 1 over s squared. Awesome. And you can see some pattern maybe, and if you want on your own, you can try a Laplace of t squared and see if you can see a pattern from there. And I'll generalize that in the next board. But for right now, let's move on to this next example, but I need to make some space here. So I'm going to erase this work on tabular and on that limit using L'Hopital's rule. So now this one is actually not all that bad at all, because notice here we have the integral from 0 to infinity of e to the 3t times e to the negative st, there we go. Since they're both powers of e, you can actually combine them as what? Well, you can combine them as e to the 3t minus st, or if you pull out the t, it's 3 minus s all to the t dt. And if you actually take a look at what we did here, it's kind of the same exact idea. It's basically the same exact idea. So what you'll end up getting is the antiderivative of this is 1 over 3 minus s, all times e to the 3 minus s times t. Evaluate between 0 and infinity. When you plug in infinity, the whole thing becomes 0, like we've been seeing. This is kind of the common trend. Minus, when you plug in 0, you get 1 over 3 minus s times e to the 0, which ends up being just, well, negative 1 over 3 minus s, which if we bring the negative down to the bottom, you actually just get 1 over s minus 3, which I think looks a little better. Okay, so now I'm going to generalize a few things, and we'll see some more properties as well. Right, so in general, we have these following values for Laplace, or these, I guess, evaluations, or you could say transformations, given a particular function. So for example, Laplace of t to any power, t to the n specifically, is actually n factorial over s to the n plus 1. And you may have noticed the pattern when we had a Laplace of 1, which is t to the 0, we had 1 over s, so the power of s in the denominator was 1 more than the power of t. And we also had that Laplace of t was 1 over s squared, so the pattern seemed like it was continuing like that. But if you actually tried a Laplace of t squared on your own, you would have got something kind of surprising. You would get t 2 over s cubed, actually. Now the numerator ends up just being the factorial of the power in general, as it turns out. And right, so when t is 0, this still holds, by the way, because you get 0 factorial over s to the 1, which is just 1 over s. Good. Now, what about this? So this is Laplace of e to the at. It's 1 over s minus a, kind of like we saw for e to the 3t. Okay. E to the at times t to the n has a Laplace transformation of n factorial over s minus a all to the n plus 1. So you kind of combine these, really. In fact, really what it does, if you multiply by e to the t inside of Laplace, all it really does is shifts your s by subtracting a inside of that s minus a, inside of that s. So here, t to the n had a Laplace of this. When you multiply that by e to the at, that s is replaced with s minus a, actually. So that's known as like a shift property. And cosine and sine, again, you can try these on your own if you like. They're actually pretty difficult because they involve, well, essentially using by parts, but twice, kind of. So you use by parts until you get a repetition of the original integral, and then you solve for that, which is kind of a method we've seen in calculus 2, hopefully. But right, as a result, Laplace of cosine ends up being this, and Laplace of sine ends up being that. So notice cosine has the variable on top, where sine has the coefficient of the argument on top. Okay? And of course, if you multiply them by e to the at, all of the s's get replaced with s minus a, kind of as I just previously spoke about in regards to that kind of shift property. Okay. So now we have these two linearity properties, which basically are inherited from the properties, linearity properties of the integral, because Laplace is defined by an integral. So here we have Laplace of a constant times a function is that constant times Laplace of that function. In other words, you can pull constants out, kind of like you can with integrals. So I'm not going to prove that, but it's actually not too hard to prove on your own if you want. Basically, you just write it down and pull the constant out, and then you get Laplace, the constant times Laplace of the function. So that's kind of nice. You can do a similar thing here. For Laplace of a function plus a function, it's Laplace of the first plus Laplace of the second. In other words, Laplace of the sum of functions is the sum of Laplace of those functions. Okay? And then I have this kind of honorable mention, which I don't think we'll really be seeing in this class at all. But this is Laplace of what is known as the heaviside function u of t minus a specifically, is e to the negative as over s, where u of t, again, is called the heaviside function, or heaviside's function. Kind of think of it as an all or nothing function. Basically, it's 0 when t is negative and 1 when t is positive, or equal to 0. So the function actually looks like this. So this is the t axis, and I guess this would be like the u axis. So u of t has this strange property that we're on this line when t is negative, and we're on this line when t is positive. That's why I say all or nothing. So either it's 1 only when it's positive, or it's 0 when it's negative. Which I know is a strange function, but as it turns out, it has a really nice transformation when you take Laplace of that function. Okay, so that's all I wanted to say here, but normally we'll be using this kind of like as a table to evaluate other types of functions when considering Laplace transformations. So let's take a look at some examples that we can use this table on as far as combinations of those. So let's take a look at that right now. All right, so I have these three examples here, and I want to take Laplace of each of these. Now again, we'll be using combinations of properties we saw in the previous board. So I guess we can get right into it, but before we do that, let me just mention that at the very end, I'm actually going to combine into one fraction. And this idea in reverse is something we'll be doing basically for the rest of the video. So I just wanted to throw that out there so you can kind of see that, but let's take a look. So using those properties we saw, first I want to use the linearity properties to break this up as much as we can. So I'll actually use them simultaneously by pulling out any constants to each term as much as possible. So I hope we can see how I got this. Not too hard to see, hopefully. If you split this up by sums, you get Laplace of 3t squared plus Laplace of negative 5t plus Laplace of 1, but then 3 and negative 5 are constants, so you can pull them out using that constant pull-out property of Laplace that we saw previously. And we know Laplace of t squared, we know Laplace of t, and we know Laplace of 1. So this is actually going to be just, well, 3 times 2 factorial, which is 2 over s cubed, minus 5 times 1 over s squared, plus well, 1 over s. So remember, the power of t is increased for the power of s in the denominator for the Laplace transform. In addition to that, the numerator will be factorial of the power, which here 1 factorial is 1 and 0 factorial is 1 as well, but here 2 factorial is just 2. So in fact, this really becomes, let me write it over here, I guess. We have 6s cubed minus 5s squared plus 5 over s squared plus 1 over s. Now what I'm going to do is I'm actually going to combine it into one fraction like I mentioned earlier. So we can multiply top and bottom of this by s, top and bottom of this by s squared, so that we get a common denominator. And what we actually end up getting is 6 minus 5s plus s squared, all divided by the common denominator s cubed. Awesome. So that I think is pretty nice. You can reverse the numerator if you want to write it in descending order, I guess, but this is fine enough. For this one, very similarly, we can pull the 3 out when we split this up. So it's 3 times Laplace of sine of 2t plus Laplace of e to the negative t. Now, if you don't remember the rules here, Laplace of sine, that had the coefficient of the argument up on top, opposed to cosine had the variable s on top. So this will have 2 on top, and in the denominator of either sine or cosine, you end up getting s squared plus the argument squared. So in this case, s squared plus 2 squared. When I say argument, I mean the thing on the inside, specifically the coefficient of the argument is what I'm talking about here. That's our b from the previous board. Now Laplace of e to the at was 1 over s minus a. Now here s is technically negative 1, because it's e to the negative 1t technically. So we can write this as 1 over s minus negative 1, which is of course just 1 over s plus 1. So actually what we get here after simplifying a bit is 6 over s squared plus 4 plus 1 over s plus 1. So what I'm going to do to combine these, I'm going to multiply top and bottom by the opposite denominator. So this top and bottom by s squared plus 4, and the first one top and bottom by just s plus 1. Like this. Perfect. And now after a little bit of combining, what we end up getting in the numerator is just, I'll leave it factored actually, s plus 1 times s squared plus 4. And that's in the denominator. And in the numerator, we would get 6s plus 6. And here we get s squared plus 4. So in total, that's s squared plus 6s. And then for the constants, we had 6 and 4, but 6 plus 4 combined to 10. So I hope that wasn't too crazy, but yeah, this is what we end up getting for this example. Awesome. So now let's see if we have space here for this last one. And if you haven't seen this before, this is known as, I believe this one is sine. I'm trying to think of, yeah, I believe it's sine. So this is actually called hyperbolic sine, or I guess sine hyperbolic of, in this case, it's of 5t. So it's kind of a strange thing, but there are 2 of these. There's sine hyperbolic and cosine hyperbolic. There's actually more. This is something that could have potentially been spoken about in a calculus class, but you may or may not have seen it, just kind of depending. But yeah, I'm not going to talk about it too much. I'm just kind of mentioning that. So in fact, it may be the other one. It may be cosine. I can't really remember off the top of my head, but I'm pretty sure it's sine. But again, it doesn't really matter. What I'm going to do is actually I'm going to apply these properties, split things up, and let's see what we can get. Okay, so the first thing I'm going to do, if you split this up as 1/2 times the first one minus 1/2 times the second, and then split up and pull the 1/2s out, you get 1/2 times Laplace of e to the 5t minus 1/2 times Laplace of e to the negative 5t. And this is actually pretty simple because it's e to the something times t. It's just 1 over s minus that something. So here it's going to be 1/2 times, well, 1 over s minus 5. And here it's going to be negative 1/2 times 1 over s plus 5. And we, of course, can see that kind of like we saw here. It was e to the negative 1t. So the Laplace ended up being s minus negative 1 in the denominator, which was positive. So the signs are opposite. Really? Okay, now if you want, there's a few ways that we can actually split this up, but I'm going to do this. I'm going to pull 1/2 out. And what I'm going to notice actually is that if we were to multiply the top and bottom of each of these by the opposite denominators, here we would get s plus 5 on top, here we would get s minus 5 on top. So actually if you do s plus 5 minus s, so let me write it off to the side here. I'm going to do this a little fast. But if you get s plus 5 minus s plus, or minus s minus 5 like this, after distributing the negative, what you end up getting is s plus 5 minus s plus 5. The s's cancel, so you just get 10. So on the top we'll get 10. In the denominator, we'll actually get the product of these denominators, which is s minus 5 times s plus 5. That actually foils as a difference of squares as s minus 25, s squared minus 25. And of course, 2 goes into 10 5 times, so all in all, this is 5 over s squared minus 25. So in fact, what you can say is if you had sine hyperbolic of 5t, it would go to 5 over s squared minus 5 squared, which is actually very similar to what we had for sine. The rule for sine was the coefficient of the argument over s squared plus the argument coefficient squared. But here it's the exact same thing, only minus, notice. And if we wanted to do something for cosine hyperbolic, that I believe would just be a sign change here. It's something you can look into if you want. I didn't bother including this in the previous board because I don't think we'll be talking about it too much, but it is something that may possibly come up. But notice the definition is just based on powers of e, so it's handled, I think, better just by this. So now we're going to move on to something a little different. We'll be actually doing this in reverse now with Laplace inverse. So let's take a look at that right now. Alright, so like I mentioned, we'll be doing the reverse of what we just did previously. So what we need is an inverse transform. So now enter the inverse Laplace transform. Denoted L, or I guess this kind of cursive L for Laplace. The -1, we just call this Laplace inverse. So the Laplace inverse transform is such that Laplace of the Laplace inverse of a function of s is just that function of s itself, and Laplace inverse of Laplace of a function of t is just that function of t itself. Now the general, I guess, notation you would use, you can kind of think of this as like a diagram. Let me actually use a different color to show that off to the side here. Let me actually do it here. You can say a function of t, capital F of t, when you take the Laplace of this, you get a new function, capital F of s. So we've actually seen this before. But now if you go reverse now, let me use a different color like purple or something like that. You can actually go in reverse now by considering the Laplace inverse. That's kind of what we're doing here. Now this is if you take the Laplace of the Laplace inverse, you get back to where you started in either order. So if you started from here, took Laplace and then Laplace inverse, you'll get back to f of t. But then if you start here and then take Laplace inverse then Laplace, then you get back to f of s. Okay. Now there's some properties that again are inherited from the properties of Laplace. They're basically just the rewording, I guess, or reverse engineering of those properties. Now the first two are linearity properties. You can pull out constant multiples of the Laplace inverse, much like you can for the Laplace transformation. And here Laplace inverse of a sum is the sum of the Laplace inverse of those functions. And these are specific evaluations for powers of t, e to the something, and then cosine and sine, but in the opposite way you may imagine. So it's a little bit to get used to. The first one is kind of striking to some people. But again, you can kind of imagine of how you can result in 1 over s to the something. So think about, like, let's say, I don't know, s to the 6th. If we had 1 over s to the 6th, let's actually talk in terms of this diagram I mentioned here. So I want to take Laplace of something to get 1 over s to the 6th. Now remember from what we saw previously, well, what do we need? We need the power to be 1 less than this power, so it must be t to the 5th. But in doing that, what we'd actually get, you get actually 5 factorial here. So in order to cancel that 5 factorial you would get otherwise, you would need to divide by 5 factorial. And then if you look at this relationship, what we can say is now going backwards from here to Laplace, taking Laplace inverse to get to this function of t, we see that we need to subtract 1 for the power, and the factorial in the denominator must match the power exactly. So we actually get this kind of idea based on the pattern, you can say. This one isn't super surprising. Remember that e to the at had Laplace 1 over s minus a, but here this is kind of reworded a little differently. If you have a Laplace inverse of 1 over s plus a, then the result will be e to the negative at. And again, that's because Laplace of e to the negative at is 1 over s minus negative a, which is in turn 1 over s plus a. Great. And then you have kind of similar ones for cosine and sine. Notice the denominators are s squared plus b squared, where b is the coefficient of the argument of either cosine or sine. For cosine, we had an s on top. For sine, we had a b on top. Now, if there was just a 1 here, then this result would actually be 1 over b. And that's because, again, of the linearity property of constants, constant multiples, that is. If you multiply each side by 1 over b, you can bring the 1 over b on the inside here, and they cancel, and you get Laplace inverse of 1 over s squared plus b squared is just 1 over b times sine of bt. Okay, so I think that's all I wanted to say as far as these properties go in the definition. Now let's take a look at some examples, but I'll just jump into the examples. But you'll actually see that if we have a fraction that is already combined, kind of like we had from the previous 3 examples we saw, well, actually right before this, you kind of have to undo that to see where each term came from. It's a little hard to talk about, so let me show with some examples so we can see exactly what I'm talking about. Okay, so here, instead of handling all examples in one screen, I'm going to do, I think, one at a time because I think we need a little bit of space. And here we have a Laplace inverse of this fraction involving powers of s, which you kind of would expect based on our answers we got from taking Laplace of certain functions. And notice I have the denominator factored for us, which is great, because what I first want to do is I want to somehow look at the inside first and write this as essentially individual terms. So I want to split this up somehow, and what this should remind you of is what is known as partial fraction decomposition. So partial fractions is what we'll be using here. Now, partial fractions you probably have seen in Calculus 2 for sure, or even further than that, I guess you could have seen it possibly in an algebra class, which is kind of like an application of solving systems of equations. Now, partial fractions I'm not going to talk about. I have a separate video on that you can look into if you want. I may actually link that up here. But partial fractions is kind of interesting. And yeah, there are different setups as it turns out. Here we have s squared and s plus 1 in your denominator. Depending how your denominator factors tells you the different setups for partial fractions. Now again, I'm not going to talk specifically about what they are, but as we go through examples, I'll mention them, of course. So here we have s squared and s plus 1. So s squared actually is a repeated factor. So the setup would be something over s plus something over s squared, where these somethings are constant. And then for the last factor, we have s plus 1. So our numerator is a constant. The only time your numerator is not just a constant is when the denominator cannot be factored and it's quadratic or something like that. Usually that's the case. And when you have an irreducible quadratic, the numerator would be something like, instead of just a constant, it would be a linear expression. So like, imagine c s plus d, something like that. We may do an example of that later on. But for right now, let's focus at the matter at hand here. This example. So to combine this back into one fraction, we need a common denominator. Now notice, if we were to find a common denominator, it's just this original denominator. So we can multiply it here, top and bottom, by s squared, and this top and bottom by s plus 1. But notice the first one not only needs an s plus 1, but it also needs an additional s to complete that s squared. Okay, now, great, now that we have that established, we can combine it into one fraction, and what we'll get is, on the top, we'll get a times s plus 1 times b, or plus b, times the quantity s plus 1, plus c times s squared, all divided by the common denominator s squared times s plus 1. Fantastic. Now, in order to actually figure out what a, b, and c are, we have to actually compare this to the original numerator. In fact, if you compare this fraction to the original fraction, since the denominators are the same, the implication we get is that this numerator, a times s plus 1, plus b times s plus 1, plus c times s squared must be equal to the original numerator, which in this case is 2s minus 3. Now, there is a way of doing this by comparing coefficients. There's also this thing called the Heaviside method. And yes, it's the same Heaviside in which that u function was named after. And I'll actually show both here. So for the equating coefficients method, and you get a system of equations, you would look for the coefficient of s squared, the coefficient of s, and the constant coefficient. Now, for the coefficient of s squared, here it's 0, because there's no s squared. In fact, if you wanted to, you can actually add that in, plus 0 times s squared. Now, if you pick apart the s squared coefficients, here we have c, and here if you distribute this as, you get as squared. So in fact, a plus c will be the coefficient of s squared on the left, and you get 0 on the right, of course. Now for s, again, if you distribute this as times 1 is as, so that's a, plus, if you distribute this b, you get b times s. So a plus b would be a coefficient of s. And again, that's just because if you rearrange this by distributing and combine like terms, you'll have a plus b times the quantity s squared, and then a plus c times the quantity s squared, and then a plus b times the quantity s. And the constant will be, there's no constant here because they're both times s when you distribute. When you distribute this b, you get only b actually. So we get b is equal to something. Now, the coefficient of s on the right is 2, and the coefficient of b, or the constant term really, on the right is negative 3. So in fact, this system is actually pretty easily solved because we know b is negative 3. And using that information here, that would say a plus negative 3 is 2. If you add 3, you get a is 5. And then using that information here, if a plus 5 is, well, I guess if c plus 5, 5 plus c because a is 5, is 0, that means c must be negative 5. So this solves for a, b, and c. It's a little complicated, but it's not too bad, actually. Now, this is solving by what is called equating coefficients. So let me write that here, equate coefficients. Now, on the left side here, I'm going to use the Heavisides method. And Heavisides method is basically plugging in values of s that we like. So if you look at the denominator, when is the denominator 0? Either when s is 0 or when s is negative 1. So we're going to plug those in and see what happens. So when s is 0, we get 0 times, well, that just blows up to 0. That becomes b plus, well, just b times 1, because 0 plus 1 is 1, and times b is just b. C times 0 is 0, so all we get on the left is b. And then when we plug 0 here, we get 0 minus negative 3, which is just negative 3. And that gives us a b right away. And notice it's the same thing, of course. When s is negative 1, however, s minus 1, or I guess s plus 1, I should say. When s is negative 1, that's 0. Negative 1 plus 1 is also 0, and negative 1 squared is positive 1. So in turn, this left side just becomes c times positive 1, which is c. When you plug in negative 1 on the right, you get 2 times negative 1 is negative 2, minus 3 is negative 5. And that's also what we got here, c is negative 5. And now we don't have any other values to plug in that will make either factors in the denominator 0, but you can just pick any value of s actually, and you'll get an equation that hopefully is nice. So I'm going to pick s equals 1. It's a pretty nice value. When you plug it in, you get a times 1 times 2, so that's 2a, plus 2b, plus 1 squared is 1, so that's plus c, is equal to, when you plug in 1 here, you get 2 minus 3 is negative 1. Now we don't know a here, but we know b and we know c. So we're going to get 2a minus 6, because 2 times negative 3 is negative 6, and plus negative 5 is equal to negative 1. That combines to negative 11. If you add that negative 11 to the other side to cancel that out, like this. So that's this, but I'm canceling it out by adding 11. We get 2a is equal to 11 minus 1 is 10. And then finally, dividing by 2, we get a is equal to positive 5. So, right, you can use either of these methods if you want in partial fraction decomposition. I prefer this one, to be honest. And again, this is called Heavisides method. Heavisides method. And I think this is a little easier in general. It's a little more efficient, really. But this idea, I think, is pretty nice, though. And it's nice to practice with this idea because sometimes you have no choice, and you actually will need to solve a system of equations anyways, possibly. Anyways, now that we know what a, b, and c are, what we can do now is we can say that this is Laplace inverse of, the inside now can be rewritten like this, but we now know a, b, and c, so that's going to be 5 over s, from the first term here, a over s, plus b over s squared, b is negative 3, so it's minus 3 over s squared. And then plus c, which was negative 5, so minus 5, over, what was the denominator for c? It was s plus 1. Perfect. And now we can split this up using the linearity properties of the Laplace inverse and then apply what we know for the evaluations of those functions, or I guess the transformations of those functions. So just for space, I'm going to erase this and continue, and then we'll be done with this problem. All right, so you can kind of see, well, the partial fraction decomposition is the majority of the work. Because now we can split this up, pull out constants accordingly. We get Laplace inverse of 1 over s. That's an s. Now, I know my 5s look like s's sometimes, but this is an s. Okay. Minus 3 times Laplace inverse of 1 over s squared. And minus 5 times Laplace inverse of 1 over s plus 1. That should make it on the screen. Good. Awesome. So now Laplace inverse of 1 over s was going to be, I think it's, well, you have to remember, subtract 1 to the power of t. Here the power is s. So remember this property, Laplace inverse of 1 over s to the n was 1 over n minus 1 factorial times t to the n minus 1. So you subtract 1 from this power to get your new power and divide by the factorial of that. So it's almost like antiderivative, only instead of adding 1 to the power, you subtract by the power, and there's obviously some other patterns there, but then when you divide, you don't divide by the new power, but you divide by the factorial of that power, so it's pretty similar. But here we're going to get 5 times, well, 1 less than 1 is 0, and t to the 0 is just 1. And we also know Laplace of 1 is 1 over s, so that makes sense. Okay, minus 3 times the Laplace inverse of s squared. Subtract 1 from the power, we get 1. So it's going to be t to the 1 over 1 factorial, which is just t. Minus 5 times, this is 1 over s plus 1. Remember that Laplace inverse was, this is Laplace inverse, there we go, was e to the negative, whatever a was, when it's 1 over s plus a. So since a is 1 in this case, it's going to be e to the negative 1t, or e to the negative t. Awesome. So, yeah, this is just 5 minus 3t minus 5 e to the negative t, of course, and that is our answer for this problem. So, again, the thing that took the longest time really was the partial fraction decomposition. The Laplace actually evaluation, or of actually finding the transformation of the Laplace inverse, that is, that part is just kind of recognizing from the table I showed previously, and the knowledge of how Laplace works, really. Great. So we're not done. I'm going to show you a few more examples, and then finally that'll be the end for this video. All right, so now for this next example, we have this fraction, and again, the denominator is factored, as we can see here. Also notice that the degree of the denominator would be 3. If you distribute this s, you get s cubed. And the degree of the numerator is s squared. And actually, we only really consider Laplace inverse of functions whose, rational functions involving powers of s, basically, where the numerator is a smaller degree than the denominator. So that'll always be the case for the problems we'll be looking at. The details of that are kind of interesting, but I'm not going to talk about that here. Now, let's see. So we know to use partial fraction decomposition, and we also know that the setup here for this is going to be something over s, because there's no repeated factor. And then, as I mentioned previously, if you have an irreducible quadratic, kind of like s squared plus 4 is irreducible, you can't actually factor this. And it makes sense to know that we can't factor this, because if you could factor it, it would mean that s squared plus 4 would actually have a 0. So for example, consider s squared minus x squared minus 4. So x squared minus 4 can be factored as x minus 2 times x plus 2. But this is just a particular example. Now notice that it has zeros, meaning that if you set x equal to 2 or negative 2, then this actual expression would be 0. Because you can see when x is 2, that's 0. When x is negative 2, that's 0. But notice also, if we have x squared minus 4 is equal to 0, then we can solve for that by adding 4 to the other side and then square rooting to get plus or minus the square root of 4, which is 2. So there's two ways of finding zeros, one by factoring and one by solving for x squared in this case and then square rooting. And the reason why I bring this up is because this is a way to connect finding a solution and factoring. Now, with that being said, this denominator s squared plus 4 can't be factored, and the way to show that is to show that it has no real zeros. So if you were to actually do the similar thing here, since it's s squared plus 4, subtracting 4 would give you s squared equals negative 4. So as a result, you get s would be equal to plus or minus the square root of negative 4, which is 2i, which is imaginary, so it doesn't factor over real numbers. In fact, anytime you have s squared plus a number, then you wouldn't be able to factor that. So long story short, if it's s squared plus a number, it cannot be factored. And the reasoning there is because it would have imaginary or I guess non-real zeros. Anyways, the setup for partial fractions is that, let me write PFD here for partial fraction decomposition. The numerator of this in the setup is not just b, but it'll be bs plus d, because we want it to be 1 degree less than this denominator. The degree of this is 1, the numerator is degree 0, so it's constant. And I guess the only exception to the rules are when you have repeats. Like remember the previous example we had s squared, but that was a repeat of s. So it was a over s plus b over s squared. But here s squared plus 4 is not a repeat, it's actually one factor, and it has, well, degree 2, so its numerator must have degree 1. Okay. So now how do we combine? We can combine by multiplying this by that denominator to get a times s squared plus 4 plus b times s plus d, multiply by the other denominator s, and then combine into one fraction like this, where the denominators, well, the denominator here is the product of these denominators, is what I was trying to say. Good. So we have this finally. Now remember that our setup gives us that if you compare this to the original fraction, really the denominators will always be the same, so that means the numerator is what we're actually comparing. So we have the equation now, a times s squared plus 4 is, plus bs plus d times s is equal to the numerator s squared minus s plus 2. Now again, what method you want to use is up to you, but I like Heaviside method, so I'm going to use Heaviside method. Now in the denominator, either this is 0, in which case s is 0, and I don't know why I put d here, and in fact should have used bs plus c, but for some reason I used d, so my mistake there. But it really doesn't matter, you can call the letters whatever you want, but it really should be in alphabetical order. So I made a misstep there for some reason. But anyways, if we plug in s to be 0, what do we get? Well, that becomes 4a because 0 plus 4 is 4. And here that becomes 0 because it's b times 0, which is 0 plus c, so it's c, but then times 0 is 0 anyways. When you plug in 0 here, we get 0, 0, and 2, so that's 2. So dividing by 4a is actually 1/2. Okay, not too bad. But now there's a problem, and the problem is, what can we plug in for s now? Well, since s squared minus 4, s squared plus 4 that is, has no real zeros, and I don't want to plug in imaginary numbers, we don't get anything else from setting the denominator factors equal to 0. But remember, you can always plug in nice values. In fact, you can plug in any value you want as long as you haven't plugged it in already. So I'm going to plug in 1 and see what happens. When we plug in 1, we get, well, that's going to be 5, that's going to be b plus c, and that's 1. So there's going to be 5a plus b plus c is equal to 1 minus 1 cancels, and you just get 2. Now the nice thing here is since a is equal to 1/2 already, and we circle that, then really what we get is 5/2, because 5 times 1/2 is 5/2, plus b plus c is equal to 2. But if you subtract this 5/2 to this side, you get 2 minus 5/2, which is negative 1/2. And I know that, of course, because 5/2 is 2.5, and 2 minus 2.5 is negative 1/2. So even though we don't actually get a solution necessarily for b or c, we get a nice equation. So now we're going to plug in another value for s and see if we get another equation. I'm going to plug in negative 1. You can plug in 2 if you want as well, but the numbers are kind of a little larger. So negative 1 I think is fine. Negative 1 squared is 1 plus 4 is still 5a. Plus, when you plug in negative 1, that becomes negative b plus c. But it's times negative 1, because s is negative 1. So if you distribute this negative, then the signs actually change to plus b minus c now. So this is really plus b minus c, like that. Good. Equals, now on this side, when you plug in negative 1, you get negative 1 squared is positive 1, minus negative 1 is actually also positive 1 because of the double negative. So you actually get 1 plus 1 is 2, plus 2 is 4 total. Great. So now again, a is 1/2, so this is 5/2, which is 2.5. If you subtract that over, you get b minus c is equal to 4 minus 2.5 is 1.5, or as a fraction 3/2. Great. So we have these two kind of nice looking equations, and we can for sure solve this system of equations. And in fact, this system is actually pretty easily solved by just adding straight down. And you can see when you add straight down, the c's cancel out. So let me show that when you add these, you end up getting this cancellation of c's. So you get b plus b, which is 2b, is equal to -1/2 plus 3/2. That's 2 over 2, which is 1. So that means b is also 1/2, like a was. Great. And now, well, we can plug back into either of these. Let's plug into the top one. So if b is 1/2, then that means 1/2 plus c is -1/2. So that means if we subtract that 1/2 to this side, we get c is -1/2 minus 1/2, which of course is -2 over 2 or -1. Fantastic. So now we have values for a, b, and c. So we can write the inside now of our Laplace inverse as a over s, so it's 1/2 over s, plus bs plus c, so 1/2 s minus 1. So it looks a little funny, but that's okay, over s squared plus 4. So now, much like with the previous example, I'm going to erase all of this partial fraction business, and we're going to continue using some Laplace properties, as well as some knowledge on Laplace transformation, actually kind of like evaluations. So let's take a look at that right now. Right, so I erased everything basically up to this point, and now let's split it up and let's see what happens. Now before I split it up, I actually want to split this up a little further, but I'll actually do that in the next step. So let me show you. So I'm going to split this up over the sum, and I'm going to pull out constants. So this is going to be 1/2 times Laplace inverse of 1 over s, plus 1/2, so you'll see what I mean in a second, times Laplace inverse of s over s squared plus 4 minus Laplace inverse of 1 over s squared plus 4. So that may have been a little hard to follow, so let me try to elaborate a little bit here. If you split this fraction up in the inside of this Laplace, we have 1/2 s over the denominator s squared plus 4, and then minus 1 over s squared plus 4. Now that should really explain any confusion we had here. Because now Laplace inverse of this, you can pull the 1/2 out, you get that left on the inside. And then here you can pull the negative because it's a constant -1. Pull that out of the Laplace inverse and we get that on the inside still. Fantastic. So the s squared plus 4 should give you cosine and sine vibes. Now specifically we want s squared plus something squared. Since 4 is 2 squared, this is going to remind us of cosine of 2s. Or it's really 2t. So cosine of 2t or sine of 2t. And in fact, we actually have each of these here. So let's see. But before we get to that, 1 over s, remember, the Laplace inverse of 1 over s was just 1. So this is just 1/2. So the first term is just 1/2. Plus 1/2 times, now, Laplace inverse of s over s squared plus 2 squared is just cosine of 2t. That part hopefully isn't too bad. And it's because the numerator is s. Here, this is where things get a little funny, and I kind of spoke of this previously. Now, if you were to take Laplace of, let's say, sine of 2t, you get 2 over s squared plus 2 squared, like that. But we don't have a 2 on top, we have a 1 on top. But not to worry, if we multiplied and divided by 2, then we'd actually get that. So if we multiplied the inside by 2, we get this. And if we divide the outside by 2, we get a 1/2. And then we get our sine of 2t. Now, I know sometimes I write parentheses for sine and cosine, sometimes I don't. But it really doesn't matter. It's kind of up to us to know the difference. But there's no difference. It's just I'm being lazy sometimes, that's all. Great. So I hope that's okay. Now again, if you wanted to check this, you can take Laplace inverse, you can take Laplace, the original Laplace, of this and see that you indeed get that. Right, Laplace of 1 is 1 over s. Laplace of cosine of 2t is s over s squared plus 2 squared. And Laplace of sine of 2t is 2 over s squared plus 4. Bringing the 1/2 in, we'll cancel this 2 and just leave us with 1 over s squared plus 4. It was negative, of course, so it's negative. And yeah, so this is actually going to be our answer now. All right, so now I just want to do one last example. So let's take a look at that one last example right now. All right, so this last one I'm going to do is not actually going to be as complicated as the previous two, believe it or not. but it's just going to be a little tricky to start off. So the first thing you'll notice is that we have this fraction like we kind of expect. We want to take the Laplace inverse of that. But of course the denominator can't actually be factored. There are no two numbers that multiply to 8 and add to 4, unfortunately. And remember that we want our denominator to be factored, and usually it will be factored for us, actually. But here it's not factored for us. In fact, it can't be factored like I just mentioned. So what do we do? Well, honestly, there's not really too much you can do, but in this case, what you actually kind of can do is you can try to complete the square and write this as something squared plus something. So let me show you what I mean by that. So I'm going to complete the square here. And if you don't recall, to complete the square, you want to ignore the constant term. So we just have s squared plus 4s. And you want to figure out what this number is in order for this to be written as a square. Now I know it's s plus because our middle term is plus. And if you kind of remind yourself of how some binomials expand, think of like s plus a squared. That expands as s squared plus 2as plus s squared. And very similarly, if it was s minus a quantity squared, then only the middle term would be a negative. So in other words, if your middle term is negative, then this will actually compact as a square with a negative in the middle instead of a plus. And what you kind of notice here is that whatever this is must actually be half of the number in front of s. And in fact, here half of 4 is 2, so this must be a 2. But notice if you expand this out, according to that, you get s squared plus 4s indeed, but then plus 2 squared, which is 4. So this unknown must be 4. Okay? And the nice thing about this is, since we had 8, then 4 plus 4 is 8. So what we've done is we've written this in a way such that we have a completed square. Which I know sounds a little funny, but that's actually what you would do in this case. So we can actually rewrite our denominator as s plus 2 quantity squared plus 4. Okay? So again, if you can factor the denominator, you can always do something like this. And hopefully this is not a minus, it's a plus. If it was a minus, then it gets a little weird, but it's still kind of doable. But I'm not going to talk about it. Let's just kind of... And in fact, if it is a minus, then that means it actually can be factored. Because then you can write this as a difference of squares. The square root of this minus the square root of that. And then the square root of this plus the square root of that. But of course, if you can't square root this, then... Well, I mean, it can still be factored, but you'll have weird radicals in your factorization. But anyways, I'm getting a little bit on a tangent there. So now what we can say is our denominator is of the form s plus 2 squared plus 4. Now, I actually haven't written this in the Laplace inverse table I showed you for values, but I did for the Laplace of values. So, for example, if you remember, we said Laplace of e to the, I think it was e to the at times, let's say, sine of bt, or cosine of bt. Doesn't really matter which one, but for right now, let's take a look at sine. So remember the rule for sine was b over s squared plus b squared. But since we're multiplying by e to the at, if you don't remember what that does, that shifts all of the s's by a factor of a. In other words, your s gets replaced with s minus a. In fact, the exact same thing happens here, but in reverse. So here our a is negative 2. Because s minus a, if a is negative 2, would be s plus 2. So in fact, what this has no choice to be is, if you take a look at this being 1 over s squared plus 4, that should remind you, actually we saw exactly what that was from the previous example. That was 1/2 times sine, 1/2, sorry, not 1 over s, times sine of 2t. And I know it's 2 because 4 is 2 squared, but it's 1/2 because the denominator needs to be a 2, but it's a 1, so you divide by 2 on the outside instead. But the fact that we have s plus 2 instead of s, then that means we must have e to the negative 2t multiplied to this because of that shift in s. And that is the answer. So this wasn't as complicated in the sense that we don't have to use partial fractions, but because it involves completing the square and recognizing some things, I thought it was a very suitable last example to discuss for this section on the Laplace transform, and of course on inverse Laplace as well. In the next video, we'll actually be taking a look at why we're talking about this and how it applies to differential equations. It's going to be quite nice. And yeah, it's going to be a lot of fun. So I'll see you in the next video. Thanks for watching. Hope you all enjoyed, and I'll see you then.